All right, so in this video, we're continuing exercise 10, but we're going to be looking at a far better and a far more efficient approach towards finding the square root. So in the first video segment for this exercise, we looked at exhaustive enumeration, and the idea was to start at 0 and determine a relatively small stepping point and test every single value along the number line until we found the actual value whose square was within epsilon of the user's input. And I went through a lot of examples, and I just kept one of the printout statements here with an epsilon of 0.001, which was a fairly robust value, but certainly not incredibly precise. If I tried to figure out the square root of 144, which we know is 12, it actually took me, let's see, over 11 million iterations to find that that square root was 11.999, which again is not perfectly 12, but it's accurate enough according to our epsilon. That takes, on my machine, it was taking about 10, 12 seconds. That's an enormous amount of time to figure out the square root of 144, and we'd like to be able to bring that down a little bit. And one of the reasons why it's so much is that this method sort of takes a really naive approach. It starts all the way at 0 and it proceeds to the right in hops, right, in steps. And if I'm trying to find, for instance, that this goes all the way out to 144, not drawn to scale, right? If I guess, maybe my initial guess is 0.0001. That is, when I square that, that is absolutely nowhere close to 144. And instead of actually learning from that, really, we just check 0.0002 next. All right, that's exhaustive enumeration. It's a very naive approach in that by looking at this value and realizing that it's not coming anywhere close to this value when squared, if we were smart, we'd jump. We'd go further. Maybe we'd jump over and check if 5 squared was equal to 144. And of course it isn't, but it's getting a lot closer, right? And by gauging that, we can kind of make bigger jumps, right? And so, and the method that I want to work on in this video kind of uses that sort of logic, but instead of starting all the way at the very beginning, it starts in the middle, and it's called the bisection method. So I'm going to erase all this stuff. And I'm going to say, okay, well, I'm going to calculate the square root of 144. And let's just say that based on some knowledge, I know that it's between 0 and 20. Certainly I know it's between 0 and 144. I don't really have enough room to write the 144 out here, so we'll just leave it somewhere like this. The bisection method works on the idea that I'm going to split the difference. I'm going to go right in the middle, all right, and I'm going to take a sample right there. And I'm going to say, well, what is 10 squared? Right? Well, that's equal to 100. Right? So where could the square root on a number line exist? This area is out, right? Because any number less than 10, the square of that number is going to be less than 100. And I'm looking for 144. All right? 100 is less than 144, which tells me that the amount or the region of the number line that could have the square root of 144 is only to this right side. So in one sample, I've knocked out, in the old exhaustion method, exhaustive enumeration, I've knocked out maybe thousands, millions of samples, right, in one iteration. Next, I'm going to repeat the same process. I'm going to go to the middle of the remaining section, and I'm going to calculate 15 squared, right? And so I don't know off the top of my head what that is. 15 times 15, right? 225. So that's quite a bit bigger than 144, right? Which tells me that anything greater than 15 will also be greater than 144. So this part goes out. And now I'm going to go to the 12.5. And 12.5 is going to be obviously a little larger than 144. We know that just because we understand what the square root of 144 is. So that's going to knock that out. And I'm going to keep splitting the difference, and eventually I'm going to get to 12. Okay. The idea here is that I'm going to take my previous sample, and I'm not just going to say yes or no, is it the right answer, but I'm going to use it to knock out or to eliminate many, many, many other numbers from consideration. The key to this algorithm is not a step, actually. I don't need to think about a step. I will need to think about an epsilon value. I'm still going to get, answers like, 12.0001 as being reasonable. But the other thing that I need to think about is, well, what was this initial bracket? I said, oh, well, it's got to be between 0 and 20. The 20 is probably artificial. What we can do is we can bracket the number line from 0 all the way out to whatever x is. In this case, the 144. Right? And we'll just do the bisection. And you might say, well, that's kind of naive. This is going to be farther from the actual answer. That's true, but we're probably going to recover from that very quickly. So what we want to try to minimize and try to compare is, this 11 million iterations for 144. Let's see how much better we can do with the bisection method. All right, so I've got my exhaustive enumeration. I'm going to keep a lot of this, so I'm not going to start fresh. What I'm going to do is I'm going to get rid of this step, and I'm going to come up with a bracket, right? So I've got the low is equal to 0. That's the lowest value I'll consider. And remember, as I proceed, the low value might not be 0, right? We might decide the low value is 10. It's 10 between 10 and 20. So that'll adjust. The high value could be equal to whatever the user typed in, x. One thing, and the book points this out too, that you want to remember is that if the user typed in a number less than 1, its actual square, or its square root will be greater than itself. So if the user types in 0.1, the square root is actually 0.01. So I'm sorry, if the user types in 0.01, the square root is 0.1. So we need to be careful with that. We actually should do so we need to make sure that we only use no value between 0 and 1. So what I'm doing here is simply taking the maximum, right? So if the user types in 0.01, I will use 1 instead as the high value, and that way I'll be able to still find the answer. If the user types in some value greater than 1, of course, I'll use that value. Okay, so we're still going to use number iterations. The only difference here is that I'm not going to start at 0. Remember, we start right in the middle. So the middle of those two brackets is just high plus low divided by 2. Of course, since low is 0, I really could have just made that at high divided by 2. Later on in this loop, I'll be splitting values where the low isn't necessarily 0. So I'm just kind of trying to be a little consistent. The second question is, well, what's our stop condition? In this case, we're still going to stop when we found the value that's between or that is within epsilon of the square root of x. This second condition, if you remember in exhaustive enumeration, it was to guard against the fact that we might sort of shoot right past the actual value. So if we were shooting for 12 and we happen to skip past it, we could keep going on forever. We don't actually need that this time. Because we're not going to keep going in an increasing direction. We're not blindly increasing the value. Once we go past the actual, or once we find a value that's higher when squared, that's higher than x, we're going to go back. We're going to go back into a smaller number. And we can continue to divide the search space in half indefinitely until we find an answer. So what you'll notice here is that we don't actually have to define a maximum number of steps. Or stop condition artificially. So I'm going to take that off. I'm still going to count how many iterations I have, but answer is not going to just increase by some artificial step. Now we have to determine which bracket we're actually in. So if answer squared is greater than x, that means that the actual value, the actual answer that we're looking for, must be less than this current one, must be less. So if we go back here, let's kind of clear out some of this stuff. If we've guessed, let's say, if we're trying to find the square root of 81, per se, and here's our guess, that's our answer. Well, if that's 100, all right, that's greater than 81, meaning that it must be over here. Right, so we're going to recompute the new value. Low is going to remain here, but now our high value is going to be this midpoint. So I'm going to reset high to be whatever answer currently is. Else, that means I was in this region, right? So let's say I was trying to find the square root of 144, right? And I guessed 100. Well, now I know that since 100 is less than 144, that this region's out and I have to search this region. The low has now become the answer and high remains whatever it was. Okay, so once we've determined the new high and low points, we need to find the new answer because we want to actually go through and now come up with a new midpoint, right? So it's going to be halfway between high and low. And whether or not low is 0 or not, it doesn't make a difference. We just need to come up with that new answer. Okay, so we've got answer equals, and again, this is consistent with what I did above, high plus low divided by 2. And that'll give us the midpoint between high and low. We can still print out the number of iterations. It turns out that we're actually never going to be unable to find this square root, so we can kind of just, we can probably remove that, but for debugging purposes, I'll leave it for now. We'll put bisection, of course, instead of exhaustive enumeration. All right, so now I've changed the value, and let's do 144. And right away, what we see is just an absolutely incredible drop from over 11 million iterations, and that was admittedly at a pretty high epsilon or pretty low epsilon, to now only 20 iterations. If we try other values, we can see 511 in just 21 iterations. We can see 1, 2, 3, 4, 5, 6, if I can type that correctly, in just 34 iterations. That was the value that when I tried with exhaustive enumeration in a past video, I simply had to let it run for a while. I paused the video recording and just it ran for an extraordinary amount of time. And we were ending up with literally billions of iterations. So, you know, is it as straightforward of a calculation? No, it is not. But is it worth it, right? Is it worth the added complexity? And clearly, the ability to compute this is just drastically better. So you're seeing for the first time probably why sometimes computer scientists will develop rather complicated solutions to problems, even when there are easier ones at hand.